Hi everyone, welcome to Unit 11 review. This is for your upcoming test. I decided to do just the evens, and the answer key will be online. So if you have any questions on the other ones, feel free to look there. But this will be a nice representation of one of each type of problem that you might be expected to know for your test. Okay, don't forget that the test is cumulative, so this is only covering the trig portion. And please excuse my voice. I've just been getting over being sick, so I hope it's not too annoying. It sounds all stuffy. Okay, let's get going. Number 2, the expression sine squared over cos plus cos b is equivalent to. Well, this is all about identities. So I'm taking a look at all of these and saying, what can I do to make them more like sine and cosine, right? So this guy right here, I know that's equivalent to my Pythagorean identity of 1 minus cosine squared theta. However, in the context of this problem, it's not going to help. But I want to show you my thought process anyway. Okay, that doesn't get me any closer to reducing this identity to the basics, to just sine and cosine. So this one actually requires adding. You're adding two functions, two fractions. So look, let's put this one over 1. Let's find a lowest common denominator. So I believe that would be cosine b. And in order to get the denominators the same, this guy's okay. He has it, cosine b. This one does not. So we would want to multiply top and bottom, in this case, by cosine b. Now trig functions are just like x and y. If you're going to multiply cos times cos, that's like, x times x, you would get x squared. So in this case, you'll get cos squared. So now let's see if this helps us out a little bit. So sine squared b over cos b plus cosine squared b over cos b. Okay, common denominators have been achieved. So let's add our fractions and put the result over a single common denominator. And now maybe this can help us out, since our first choice wasn't really that helpful. Cool. Okay, so where are we? Sine squared b plus cosine squared b over cosine b. Oops, sorry. Let's go check our Pythagorean identities again and see if this can be reduced to anything or replaced by something. And if you look at your identities, you'll see that sine squared plus cosine squared is really just equal to 1. So that's nice. We still have cos on the bottom. But we now know this, 1 over cos, is actually equal to secant, which is nowhere. That's funny, but it is right here. Sorry, A, 1 over cosine B. So I guess this was taking it way too far. Either answer is acceptable. I prefer secant, but anyway, so to recap, basically when you're working with identities, just try to get everything to sine and cos. And if you ever see any squareds, check out your Pythagorean identities. That's what we did at first, but then we found out it wasn't very helpful. So we went back to basics and said, okay, we're adding two fractions. Let's get common denominators, and let's see if that helps. And in fact, it did. It brought us to this Pythagorean identity, which we set equal to 1, and our common denominator was cos, and that's choice A. Maybe you might want to take it further and say, I recognize this as a reciprocal. It's actually secant. All right, very good. Next question. Number 4. Okay, this is multiplication. So Let's see. Cosine times secant, cosine times negative cosine. Let's follow the rule here. Let's try to make everything sine and cos. So cosine times secant is a reciprocal function, which is 1 over cos. Cosine is just cosine. Okay. Now, when we distribute, you'll see that cosine times 1 over cosine will actually cancel out the coses, leaving us with just 1. And then the second time we multiply, we have cosine times cosine, which is cosine squared, theta. Okay, so we took care of our multiplication. Now, we want to get everything down to its basics, sine and cosine, and wherever we see squareds, we always check the Pythagorean identities. So, the Pythagorean identity that has cosine squared in it looks like this. Sine squared theta plus cosine squared theta equals 1. So what I want to do now is just rearrange this Pythagorean identity to look like this, right? So I'm looking for a positive 1. It's right here. Now I'm looking for a negative cosine squared theta. So to do that, I can just move this 1 over. So let's subtract cosine squared theta from both sides. And now it will look exactly like you wanted it to. Sine squared theta equals 1 minus cosine squared theta. So by simply applying the rules of equations, where you can move terms to either side just by changing their sign, we were able to find a Pythagorean identity that looked just like we needed it to, 1 minus cosine squared theta. And when we did, we found out that that was equivalent to sine squared theta. That's our answer. Choice C. Okay, 6, the terminal side of an angle. That just means where it ends. Terminal side of an angle. Think of an airline terminal. It's where your flight terminates. It's where it's over. So terminal side. That just equals the end. So let's draw a graph. Let's put the quadrants in. Quadrant 3 is where this angle terminates. So let's go draw some random angle that terminates in quadrant 3. Okay, that's what it means to terminate in quadrant 3. How much are you is the question. Well, let's go through the choices. Negative 255. That means we're going to go in the negative direction. Negative 90, negative 180. The next stop would be negative 270, so we would stop right about there for negative 255. That is quadrant 2. So something to remember when you do angles and quadrants, even if you start out negative, going to the bottom, it doesn't change the order of the quadrants. These quadrants are locked in stone. This will always be 1, 2, 3, and 4, regardless of the direction you travel. Nothing changes like that. The only thing that changes is the angles. You know, if you go down first, the first stop is negative 90. You wouldn't say positive 270, you know, because you're heading down. All right, so that guy's no good. Negative 240 kind of sounds the same to me, right? I mean, let me just erase this guy here. 240 is just same story. Negative 90, negative 180. I don't want to get to 270, so somewhere in here is negative 240. So that's also quadrant 2. We don't want that one. Let's check out choice C, 120 degrees. Okay, so that guy, in standard position, positive angles open upward. So that would be positive 90. Next stop, positive 180, so let's stop before we get there. Somewhere in here would be 120 degrees. Okay, that's also the second quadrant. No good. So as you can see, it is choice letter D, but let's work it out. We're here anyway, right? Okay, negative angle opens downward. There's negative 90. A little bit past there, negative 110. That's quadrant 3. That was what the question was asking for. So choice D is our correct choice. Number 8. Which of the following is coterminal? So coterminal just means ends with. So to get there, there's a million answers. It's limitless. So you can find them by just going around the block one more time in any direction. So let's say this. You can find them by adding or subtracting 360 degrees. Right? Because check this out. Coterminal, you have an angle. Let's say, for example, the angle was 30 degrees. Well, who else is coterminal with me? How about this angle? How about I go around a block once? That's 360, right? And then I stop right here again. So if I took my 30 degrees and I added another 360 to it, 390 would land on the same exact line. Well, let's go the other way. I'll show you an angle in blue. Let's start standard position, but negative. We'll go down like this, negative 90, negative 180, negative 270. Let's land right on that line. What would I be? I'd be negative 330. Now here's a way to figure that out. Take your 30-degree angle and subtract 360. That's negative 330. Both of these angles are coterminal with 30 degrees because they end on the same spot. And to figure out what they are, if you can't draw, add or subtract 360 degrees. So our question here is 915 degrees. So I'm not going to graph that because that's a few times around the block and that'll get very dizzy. So here's my 915. I see all of these answers are pretty small. So I'm not going to add 360. That would be a waste of time. I'm just going to start reducing by 360 degrees. So for this one, doing it by hand here, sorry. That looks right. 555. Okay, not a choice. 555 is coterminal with 915, but so are a million other ones, and we want one that's listed here. So let's go another 360 degrees around the block and see what that gives us. It's 5, that's a 4, that's a 15, that's a 9. That would have been a 4, minus 3, 1. 195. Is that here? Ha, yes. Perfect. So 195 degrees is coterminal with 915. And so are a million other angles, negative and positive, all over the place. Just remember, 360 is the number you're looking for when it comes to coterminal. Okay, I have 600 degrees, and I want to write it into radians in terms of pi. Very cool. So just remember this. When you want to go from degrees to radians, put the pi on top. So look at what we're saying. Ready? You want to go from degrees, right? So we were given 600. Just put it over 1 to make everything line up nicer. Now if I'm going to radians, I always say pi's on top. Okay, so let's put pi on top and 180 on the bottom. Now this just becomes multiplication. You can either reduce the 600 and the 180 right away, or what I prefer to do is just multiply it. 600 pi over 180. Now in your calculator, you can just put in 600 divided by 180, and then math enter enter, which will give you your nice fraction again. Okay? So 600 divided by 180, math enter enter, and you'll see that you get 10 over 3. Put the pi back, and there's your answer, choice B. Now for question 12, we're going just the opposite, right? We have radians, and we want to go back to degrees. So when converting from radians to degrees, put degrees on top, right? The last time we put pi on top, let's just put degrees on top. Let's see what that means. Okay, we have 10 pi radians. So 10 pi. Again, put it over 1, makes it look nice. We're going to multiply by degrees on top because we want to get to degrees. So we put 180 upstairs and then pi on the bottom. This generally works out nice because, as you can see, these pi's cancel out. And then you just simply multiply what remains. And in this case, that's 10 times 180, which is 1800, over 1. I like this radian question because it doesn't have pi in it. You know, radians don't always have to be in terms of pi. It's just that if you happen to have 3.14 radians, you've got this gorgeous half circle. And that's why we always use radians in terms of pi's, you know? But you could just have a radian laying around, or in this case, negative 1.5. It just doesn't really change much. It's just, what do you do with that pi at the end, right? Because you'll remember this, going from radians to degrees, degrees are on top. So you're going to take your radians, put them over 1, and multiply, as we did in the last question, by 180 degrees over pi. So you'll notice there's no pi's to cancel. But that's okay. We're going to multiply negative 1.5 times 180. And at the end, divide by pi, which is actually a button on your calculator. And it's 3.14, give or take. Okay? So let's do that. 1.5 times 180. Negative 270 degrees. But I still have that pi on the bottom. And we want it to be the nearest tenth of a degree. So we're going to take the 270 and divide by pi. Now pi on your calculator is right above division. It's the caret key. You have to hit second caret. And this is what I get. 85.94336. So to the 10th is 1 decimal. And that's a 4. 5 and above, give it a shove. So if it's below 5, we leave it alone. Here's my correct answer, 85.9, choice C. Just to recap, radians do not always have to have pi. In fact, as a goof, let's just figure out what the heck 1 radian is, right? Just stick with me if you're interested, just so that it sticks a little more. 1 radian, right? How many degrees is that? Just off the top of my head. Let's work this out. We know 3 radians is 180 degrees, right? Because pi radians. What's 1 radian? Okay, so 1 radian times 180 over pi. Okay, the pi's don't cancel, and that's okay. We just multiply, and you get 180 divided by pi. So in my calculator, I'm typing 180, I'm dividing by pi, and wouldn't you know it, I get 57.2957 degrees. So just between friends, let's call this 57.3 degrees. That's actually a radian. And if you notice, about 3 of those would be roughly 180 degrees. So it is possible just to have radians. You don't always have to have pi radians. Be wary of that. Okay, cool. Thanks for sticking with me on that one. Number 16. Talking about, this is unit circle stuff, right? Picture this right here, like a unit circle. What are the coordinates of P? So when we learned about the unit circle, it was important to know that x and y actually correspond to the cosine and the sine of whatever angle has been drawn in standard position. So, well, there it is. That's the answer. Spoiler alert. Point P, which would be known as x comma y, right, actually stands for cosine sine. And here's a way I memorize this. X comes before y, right? So that's alphabetical right there. Did you notice that cosine and sine are also alphabetized in that way? So that's just a silly way that I remember. X comes before y in the alphabet. Cosine comes before sine in the alphabet. Hopefully that helps. Okay, another unit circle question. I'm looking at 30 degrees. In the accompanying diagram, circle O, diameter, QA is 1, measure of BOA is 30 degrees. What are the coordinates of point B? Okay, remember, coordinates on a unit circle are cosine, sine. So if I only knew the cos of 30 and the sine of 30, I'd be in business. So if you look at your notes and you check out your unit circle chart, this won't be difficult at all. You'll know that the cosine of 30 is radical 3 over 2, and the sine of 30 is 1/2. Therefore, it corresponds to these points right there. So while we're here, let's just recall, how do you make a unit circle very quickly so that you can remember all of the exact values? Why don't we do that while we're here? Okay. So let's just focus on quadrant 1. If this was my unit circle, I would start by labeling these 2 points right here as follows. This point is 0, 1. This point down here is 1, 0. So now we have these special angles here, 60, 45, 30. And now watch how I label my unit circle so that I can remember my exact values without too much headache. I start with my 0, which is in the first position of my coordinates, right? These coordinates right here. And I count up 0, 1, 2, 3. Now I do the same from this 0, which is my sine coordinate. I count up 1, 2, 3. So now everybody's over 2. So I go in and I fill all the 2's on the bottom. And like Oprah's Christmas show, you know, where she always picks one show to give away cars and stuff, everybody gets a house. So this is the Oprah show. Everyone just got a house. So I give everybody a house, even the ones, as silly as that sounds to you, just so that I don't forget. You know, everyone's over 2, everyone gets a house. That's my way of remembering. And check it out. I just built our chart. So what was the question? 30 degrees, right? And we wanted cosine and sine. Well, 30 degrees, here you are, cosine, radical 3 over 2, sine, radical 1 over 2, or, unless you're living in West Virginia, we would call that 1/2. Now recall that just knowing the first quadrant is all you need, because all these angles over here have the same exact values. They just might be negative or positive depending on the quadrant they're in. Okay, next. Okay, when someone asks about quadrants and angles terminating in certain quadrants, they're really just disguising a very simple question with a hard one. It's just where you're positive and where you're not, right? This is just a riddle. So let's see what they're saying. They're giving us the sine function, and they're saying it's negative. Negative 3/5. Where is that possible? Okay, everybody's positive in the first quadrant. Sine is positive in the second quadrant. But the sine could be here, negative, and it could be here, negative. So we have 2 choices. Our angle could be in quadrant number 3 or 4. So as you can see, you need at least one more piece of information. And this is it right here. When someone says that the cosine of an angle is less than 1, that's just a super, super sketchy way to say it's negative. They're just trying to trick you. What does it mean to be less than 0? Well, if on a number line, anything in this direction is negative. Anything in this direction is positive. So if you hear less than 0, you're hearing negative. So where is cosine negative? Okay, here for sure. And here for sure. And that's it, right? It's always in 2 spots. So where do both criteria get satisfied? In what quadrant are both of these things showing up? Right here. So quadrant number 3 is the only possible place that you can have an angle that has a sine being negative and also a cosine being negative. That only happens right here. Reference angles. Very important to remember this. Reference angles. Couple of notes for you. Ready? Reference angles. Okay. Always positive. And always less than 90. And for those of you who are bad with symbols, let me just write this. Less than 90. Otherwise known as positive acute. Okay, we just said the same thing in like 3 different ways. Just please, it's always positive. It's always less than 90. And you find it by going to the x-axis only. So find it by looking Okay, so let's check this out. Let's draw an angle. The angle is 14 pi over 3. Okay, right there I hit a brick wall. I cannot graph 14 pi over 3. That's just not in my wheelhouse. So I always take these angles that are given to me in radian form and I convert them to degrees first. So 14 pi over 3. Now I'm going to degrees, so degrees are on top. And I figure this out first. So my pi's cancel, thank goodness, that's nice. I'm taking my calculator right now and I'm saying 14 times 180, and I get 2520 on top of 3, which is 840 degrees. Okay, so here's something else I can't stand. Who's going to graph 840 degrees? I'm going to get dizzy. So let's subtract 360 until we get an angle that's at least nice, something that's graphable, you know? I mean, you could do 840 if you want. Just for me, it's a little bit annoying. So I'm going to make it a smaller number by 1 rotation, and that's going to give me 480. You know, that's still big. I could take another rotation away from it just to make it more manageable. So I'll take another 360 away, and I get 120 degrees. That I can draw without making it too sloppy, right? So let's graph 120 degrees, which is standard position, opening upward for positive angles, 90. Next stop is 180. I don't want to go there, that's too big, so I'll stop somewhere right here. I will label this 120 degrees. Now, a reference angle. Remember what we say. Always go to the x-axis. So, wherever you land, look to the x-axis and drop a perpendicular. And look in the pocket. That's your reference angle. The reference angle lives here. Of course, it looks nice. It's tiny, looks less than 90. And regardless of what position it's in or how it got created, we're always going to say positive. So in this case, 180 was the x-axis. So I will take 180 degrees, subtract 120, and I will find that my reference angle is 60 degrees. Cool. So when I go up here and I say, hey, where is 60 degrees? I realize, oh, this is a radian question. So let me just convert my 60 degrees to radians. So remember, when you go to radians, you put the pi on top. So I get 60 pi over 180, and when I reduce that fraction in my calculator, it turns out to be 1 pi over 3. That's choice A. These questions are hopefully easy to recognize, right? Sometimes they just give you the 30 or the 60, but in any event, these are special. And they're cool because you don't really have to know much about the sides of the triangle in order to find the other sides. You know, look, you have 16 here as a hypotenuse, and you're being asked to find this side, which they're just calling x, and this side, which they're calling y. In a right triangle, I would say, let's just use Pythagorean Theorem. But you need two sides to do that. So you can't use Pythagorean Theorem. That, in conjunction with the fact that it's a 30 or a 60 angle given, I hope you recognize then, this is what you need to memorize, that this is a 30, 60, 90 right triangle. Remember, all triangles add up to 180. So, the sides of this special right triangle are in a really special proportion, and they look like this. The side across the street from the 30 degree, the smaller side, can be represented as just 1x. The side across the street from the 60 can be represented by radical 3 times x. And the largest side, always the hypotenuse, and across from the 90 degree angle, can be represented as 2 times x. So this is the way I like to write it. I write the angles here, and right below them, I write their side proportions. Now we fill in, what did they give us? They always give us one side, because we're not miracle workers, we need something. And here it is, 16. So where is that? That's across from the 90, which means it's the largest side. So I'm going to go over to my 90, drop down here, and say, okay, you are 16. Now let's see how big does that make x? If the 2x is 16, then my x is 8. And we're done. It's like so fast and really cool. You know everything now. You know this side, right? It's going to be 1 times 8. And this side is going to be radical 3 times 8. Let's pretty this up a bit. This guy's just 8. This one, if you want to go to a dinner party, you would not say radical 3, 8. You would say 8 radical 3. Pinky's out. Everyone's fancy. And this guy is 16. So there you go. We just found our sides. So the one across from the 30, the smaller one, is going to be 8. And the one across from the 60, the medium, is going to be 8 radical 3. Now that you know all three sides of this triangle, if you wanted to check your work, you can plug in Pythagorean Theorem just to make sure. It's not like we're changing the rules here with special right triangles. Everything still has to apply. If it's a right triangle, it's a right triangle, right? So this should work out. This is just a check if you're interested. Cool. Okay, another special triangle, except this one's the 45. As in the last question, sometimes they don't give you both angles. They might just give you one of these. But being that you know all triangles add up to 180, even if they only give you one 45 angle, you know the other one's 45. So here's what I do. I write down my angles, and then I write down the proportions that their sides are in. So they are also in this proportion. 1x is to 1x is to radical 2x. Let's fill in what they gave us, which happens to be across from the 90. So we quite simply just go over to the 90 and say, you are equal to 12 radical 2. Okay, so since we have this one, let's solve for x. How is it possible that radical 2 times x is equal to 12 times radical 2? Let's solve for x. Once we do this, we're done. Okay, looking to get x by itself, I divide both sides of the equation by radical 2. That cancels. That cancels. Check it out. X equals 12. The rest is easy. Let's go back to our proportions and plug in 12 for x. So the side across from the 45 is equal to 1 times 12. The side across from the other 45 is 1 times 12. And what we were already given, we know, is going to be 12 radical 2. So our sides are 12, 12, 12 radical 2. So this guy's 12 across from the 45. This guy's 12 across from that 45. And this one was given. So just by being given one side of a right triangle and knowing that they're special, you're able to find out everything else, which is really, really cool. Now, as a check, if you wanted to, you could use Pythagorean Theorem just to make sure you're right. And see if that's true. That's just a check. You don't have to do it. I just want you to know that nothing changes with special right triangles. It's still a right triangle, and Pythagorean Theorem still applies. And it's a nice way to check your answer. Okay, question number 28. Drawing angles in standard position. So, that means you have your initial side. That's all. Standard position means you start at the x-axis on the right. And if you're a positive 220, you open upward in the positive direction. So you've got 90 over here, 180, 270, 0, 360, and so on and so on and so on. So if I'm going to draw a 220, I'll start my journey northbound, passing 90. I don't want to get to 180. Oh, no, I do, sorry. Okay, I'm passing 180. I don't want to get to 270 because I just want 220. There we go. Beautiful. Cool. That's 220 degrees drawn in standard position. Okay, so let's take it one step further. Let's sketch an angle in standard position and then find the reference angle. So, again, I have no idea what this is. I can't graph that. It's just not in me. So I know how to graph degrees, you know. So let me take 5 pi over 4 and make it in degrees first, because I don't know about you, but I can't graph radians. So 2 degrees, let's see. That means degrees on top. That's what we multiply by. So negative 5 pi over 4 times 180 over pi. This is nice because the pi's cancel. Beautiful. I'm left with negative 5 times 180, which in my handy dandy calculator is going to tell me 900 divided by 4, which is negative 225. Okay, that I can handle. So, standard position, starting at the x-axis, negatives open downward. This would be negative 90, negative 180, negative 270 is coming up, so I will stop short of it, and there you go. This is negative 225 degrees. Or, sorry, negative 5 pi over 4. Now they want a reference angle. Reference angles are always positive and they are acute. In other words, less than 90. Go to the x-axis, never y, never the y-axis. So where did my angle end? Right here. Okay, so I go right to the nearest x-axis, which is right down there. This is now my reference angle. If I'm in the second quadrant, I can always say, in this case, 225 minus 180. Remember, not negative. -45 degrees. Not negative 45, always positive. So, since we're in radians, I'm not going to say 45 degrees. They gave us the question in radians, so let's be friendly neighbors and pass it back as radians. So how do you go to radians? You multiply by radians on top, or pi on top. Cool. So this is 45 pi over 180. So I take my calculator and I reduce 45 over 180 into a fraction, and I get 1 over 4. So the answer is pi over 4. That's the reference angle. Cool. Very nice. Okay, 32. Cosine of 510. Let's make that the function of a positive acute angle. Yeah, okay, so that's a very fancy way to say reference angle. So Miss Barris in her videos did something very nice. To solve this, we just do line, box, line. And over here on the left, we're talking about, are you positive or negative? Where you are. What's your function? And over here is, what's the reference angle? So check out how this unfolds. Ready? 510 cosine. Okay, Well, first of all, we need to know where we are. So 510 degrees. It's a pretty big angle. It's positive, right? So we're going to open upwards. So we're going to go around the block, 360. My next stop is 450. I'm just adding another 90, right? So 450. Okay, so 510 is going to be in here, right about there. Nice. That's 510 degrees. So my reference angle is right here, going to the x-axis. Wherever it is you end, no matter how many times you went around, negative or positive, it doesn't matter. Find your nearest x-axis, and that becomes your reference angle. It's always small, it's always less than 90, and it's always positive, regardless. Okay, now figuring this out might be a little bit crazy. This is how I do it. I had to go 60 degrees in here, as I passed my 450. I added another 60 degrees to get to 510. So that tells me that 30 was what was remaining in that quadrant, because every quadrant has 90 degrees in it. That's one quadrant. So as I passed this y-axis into quadrant number 2, I went another 60 degrees, and that left me with 30. Okay, so what's this all about? Let's fill it in. Line, box, line. Okay, so my angle ended in quadrant number 2. For cosine, is that negative or positive? Well, let's see. ASTC. Second quadrant, the only one there is sine. Everybody else is negative. So, negative. Cosine is negative. What's my function? Cosine. What's my reference angle? 30 degrees. In other words, the cos of 510 is equivalent to the negative cosine of 30. Just use line, box, line. Draw your angle, figure out where you land. Ask yourself, for the given function, would I be negative or positive in this quadrant? And that's as simple as just remembering ASTC. You put that answer right here. The next one's given. What function are you dealing with? Well, you already know that. Just write it. The third part is a little more difficult. What's the reference angle depending on where you landed? So for that, always remember, go to the x-axis only and find out what's in that pocket. Very cool. Next. Okay, so exact value. We're talking radicals. No decimals. That's what exact value means. So tangent of negative 240. Okay. So ASTC, negative 240 in standard position opens downward. So we start here and go down. Negative 90, negative 180. I'm about to hit negative 270. I'll stop short. Somewhere in here, quadrant number 2, is where negative 240 degrees lives. Cool. So what's the exact value of that? I don't know. And if I use my calculator, it's probably a decimal. So what we need to do is envision the unit circle, or the chart that you have where you remember exact values, and you ask yourself, what's my reference angle right here? What is this guy? So if I take 240 and I subtract 180, I get 60. So I'm looking for tangent of 60. And if I use the line, box, line method, I could say that my answer would be the same as tan 60, but what about the sine, right? If I'm in the second quadrant and I'm looking for tangent, would I be negative or positive? Well, in this quadrant, tangent is negative. So negative tan of 60 would be what the exact value would be. Okay, so it's up to you to remember your charts, okay? And the tangent of 60 degrees is radical 3. So being that you're in the second quadrant, negative radical 3 is the answer. That's the exact value of the tangent of negative 240 degrees. So just to recap, when the angles are very large like that, just draw them out, find your reference angle, because I think knowing the reference angle is easier than memorizing every single angle on the unit circle. So if you could just remember quadrant 1 and then just apply signs correctly, like plus or minus, that's better. So I know that the tangent of 60 is radical 3. And being that the angle lives in quadrant 2, I'm going to put a negative sign on it because in the second quadrant, tangent's negative. Okay, 36, finding exact values again. Now, again, I'm not really good at this. I'd rather go to degrees. So I'm going to convert 2 pi over 3 to degrees first, and to multiply by 180 over pi. That's how you go 2 degrees. Put your degrees on top. Okay, so those cancel, and I'm left with 360 over 3, which is 120. Okay, now that I know how to deal with. I can do 120. So I'm going to sketch 120 in standard position. Starting positive, I open upwards, passing 90, stopping somewhere in here. That's my 120. Let me find a reference angle, which is going to be 180 minus 120, 60 degrees. Cool. Now what am I in here? You know, like all students take calculus. Cosecant, you're a family friend of sine because that's a sine sandwich right there. So sine of theta under 1 is equal to cosecant theta. So whatever my sine is, my cosecant is, right? So I'm going to be cosecant positive in this quadrant. Why? Because my sine is positive. So all the reciprocals share the same pluses and minuses in the quadrants. Okay, so I'm going to have a positive. Now I just need to know what is the sine of 60. This is how I'm going to build it. Sine of 60 is radical 3 over 2. If I want to find now the cosecant of 60, I need to flip it over. Now, this guy's no good because you need to rationalize the denominator. So let's take our 2 over radical 3 and multiply it by radical 3 over radical 3. We are now rationalizing the denominator. So I end up with 2 radical 3 over 3. That's a much better answer because the denominator is rationalized. I'm going to put a positive sign on it because I am in quadrant 2, and in quadrant 2, sine is positive, as is cosecant. Cool, so to recap, finding exact values of a large angle, what you do is just find the reference angle, go to quadrant 1, figure out what the exact value is, and then apply the appropriate signs depending on what quadrant the original angle was living in. Okay, 38. Find all values, okay, of theta that satisfy the condition cosine equals 0 where theta is larger or equal to 0 and theta is less than 360. Okay. Those sound like special quadrantal angles, don't they? I mean, after all, where is cosine 0? It's on one of these axes. So let me just label those 4 that we know. based on the unit circle, remembering that x comma y is the same as cosine comma sine, right? It's alphabetical. X comes before y, cosine comes before sine. That's how I remember. So this point here would be 1 comma 0. This point here would be 0, 1, negative 1, 0, and 0, negative 1. Okay, so what's the game here? Cosine is 0. Okay, x coordinates are equal to 0. It's not this guy. Oops, it's that guy. It's not that guy. It's this guy. Okay, so in these two locations, cosine is 0. What are they? Well, that's 90 degrees, and that's 270. Now, not to be a wise guy, but it's important for you to know. You could always add or subtract 360 and you would be in the same exact spot. You would be coterminal. So there are a limitless number of angles that solve this scenario where the cosine of an angle is 0. This could be 90. It could be negative 270. It could be negative 270 minus another 360, go around the block one more time. You know, somewhere in the 500s. So that's why they were very specific, because they wanted you to just pick two angles. They didn't want you to pick something in the thousands or in the negative millions. Just wanted to stay between 0 and 360. So in this case, my solution is going to be 90 degrees and 270. Those are the two angles that satisfy this condition, where the cosine is 0. Number 40. Okay, where is cosine negative 1? So it's just like the last question I did with you, number 38. Let's graph and plot the coordinates on the quadrantal angles. This is x and y, which is cosine and sine. This one here is 1, 0, 0, 1, negative 1, 0, 0, negative 1. We're looking for cosine. That's the x coordinate, and we want it to be negative 1. Okay. Well, it's not here. It's not here. Ooh, it's this one. And not here. Okay, this is the only place that I know of that the cosine is negative 1. And that is 180 degrees. But as you know from the last example, it could be 1,000,000 degrees, right? I could just keep going around 360, 360, 360, 360, and there's 1,000,000 answers that would still get you to land on this line. So they are very specific, and they always have to be. They're going to say, just give me the angles that are between, in this case, 0 and 360. So my answer is going to be 180 degrees. Cool. Okay, so if you're given a side, if you're given a point on an angle drawn in standard position, in this case, we're talking about negative 1, right here. What are all 6 trig functions? Well, there's a lot going on here. If we connect this point to the origin, and then from the point go to the x-axis, which we always do, what you've done is created a right triangle, upside down and reflected, but nonetheless, there it is. It's a very large angle. Oops, sorry. Hello. Oh, I'm sorry about that. Let me delete that. Okay. It's a really large angle. So what we do is we just focus on this right triangle right here by using the reference angle, right? Cool. And based on that triangle, we can get all of our 6 trig functions based on this reference angle, and then just apply the appropriate signs, either plus or minus, accordingly. So let's focus on this triangle and let's see if we can't get our SOHCAHTOA, because that's really all we need. And of course, we'll flip them upside down for the reciprocals, right? So let's label what we have. We have negative 1, 1. Okay, so this side is a 1. This side is a 1. Now, what's this side? Well, let's figure it out using Pythagorean Theorem. 1 squared plus 1 squared equals our hypotenuse squared. So this would be 1 plus 1 equals hypotenuse squared. 2, square root both sides. Okay, my hypotenuse is equal to radical 2. So let's put that in. Right here. You are now radical 2. Cool. My theta is here. So this becomes opposite, adjacent, and hypotenuse. So what is the sign? Opposite over hypotenuse. 1 over radical 2. I don't like that. I need to rationalize. Final answer, radical 2 over 2. Okay, what's my cos? And we're going to go back and check the signs later. Don't stress. Okay, cosine. Adjacent over hypotenuse. Same story. 1 over radical 2. Let's rationalize. Radical 2 over 2. Okay, what's my tangent? Tangent is opposite over adjacent. So that's 1 over 1, which equals 1. Cool. So the reciprocals. Cosecant, a sine sandwich. That's going to be equal to hypotenuse over opposite. Perfect. Radical 2. My secant, that's going to be equal to hypotenuse over adjacent. Radical 2 over 1, which is radical 2. Beautiful. And last but not least, the cotangent is going to be equal to adjacent over opposite, which is 1 over 1, which is 1. Now, checking for the signs, we're living here in quadrant number 3. So, this angle is quite large, but we were using the reference angle to get all of our exact values. You're allowed to do that. It makes life very easy. However, you just have to be careful of what the implication of quadrant 3 means for all these answers. So let's go put pluses and minuses where they belong. If I'm in the third quadrant, my sine is negative. My cosine is negative. My tangent is the only one who's positive. And while we're there, cotangent, you're going to be positive too. Cool. So whatever tangent is, cotangent is. All the reciprocals, the cousins or the sisters, whatever you want to call it, they are sharing the same sign. Okay, so therefore cosecant, you'll also be negative in quadrant number 3. And secant, you will be negative in quadrant number 3. Okay, so those are your final answers for number 42. Yep, sorry, I was just checking my answers to make sure I was okay. Sorry about that. Yeah, perfect. And that's it. Listen, good luck. I really hope you do well on the test. And I hope that this video was helpful. I'm, again, sorry for the voice. Just getting over a cold. If you have any questions, please come to Extra Help.